Today, I want to talk about a comparatively minor point which is often glossed over, but will be convenient for us to know about shortly. I want to think about the velocity vector, the acceleration vector, the speed, and the magnitude of the acceleration vector for a certain particular type of vector-valued function. Taking b and omega to be positive constants, I want to look at r of t equals b times cosine omega ti plus b sine omega tj. If you split this into components, square them, and add them up, you'll find out that this is a representation of a circle centered at the origin with a radius b. Sine and cosine are periodic functions. If you'll remember from trigonometry, the period of cosine of omega t will be 2 pi divided by omega. Likewise, the period of sine t is also 2 pi over omega. The omega is going to be related to how much time it takes to make one complete trip around this circle. Using the chain rule and information that we have from Calculus 1, it's easy enough to find the derivative of the r vector, the velocity vector. I will calculate the magnitude of this to figure out what the speed is. Squaring the components, adding them, and taking the square root, we find out that the speed is the principal square root of b squared omega squared. However, we also know that both b and omega are positive, so radical b squared and radical omega squared need not have the absolute value symbols on them. As a result, for this particular vector-valued function that we're looking at, the speed works out to be a constant. It works out to be b times omega. B is the radius of the circle we're talking about, and people often call omega the angular velocity. Since the speed is positive, if you didn't know any better, you might think that you don't need to calculate the acceleration vector, but in point of fact, we do. Even though the magnitude of the velocity vector, the speed, never changes, the vector itself does. It's a tangent vector. So as we move around on this circle, the direction of the vector changes. The vector, technically speaking, is a quantity described by both its length and its direction. The direction changes, the vector changes. Calculating the acceleration vector is straightforward. We just do the chain rule again. To calculate the magnitude, we do as before. We square the components, add them up, and take the square root. When I square the negative of b times omega squared, the negative sign goes away, and I get b squared omega to the fourth, which I can then factor out underneath the radical sign. Once again, cosine squared omega t plus sine squared omega t is 1, so this will simplify nicely. B is positive, so I don't need an absolute value here. Omega to the fourth is the square of omega squared. Omega is positive, but even if I didn't know that, omega squared is positive anyway, so I don't need the absolute value on that as well. The magnitude of the acceleration is the radius multiplied by the square of the angular velocity. An observant person will notice something. The speed is b times omega. The magnitude of the acceleration is b times omega squared. That almost equals the square of the speed, except I would need to have a b squared there instead of b. I'll put an extra factor of b in, and I'll correct for it by dividing by b as well. The top of this fraction is now the square of the speed, and the denominator is the radius of the circle that we're traveling in. So if we didn't know this fact before, we do now. If I'm traveling in a circle at a constant speed, the magnitude of the acceleration vector is just going to be the square of the speed divided by the radius. Drawing my atrociously bad picture of the Earth spins on its axis once every 24 hours. Every point on the surface of the Earth goes around in a large circle in 24 hours. The largest of these circles will be on the equator. Other circles will have smaller radii. So to make the effect that I'm about to talk about as big as possible, I'll think of being on the equator. The distance from the center of my circle is going to be the radius of the Earth, which is about 6.4 times 10 to the 6 power meters. That'll be the figure that I use for the radius of my circle. One complete revolution of the Earth is 2 pi radians. It takes 24 hours to do that. 24 hours, each hour has 60 minutes, so there are 24 times 60 minutes. Each minute has 60 seconds, so one day is 24 times 60 times 60 seconds, which is 86,400 seconds. I know how many seconds it takes to go 2 pi radians in angular position. This will let me calculate the omega. Doing the arithmetic, omega works out to be about 7.27 times 10 to the minus 5 radians per second. To use my formulas, the angles have to be in radians, and I'm going to use seconds as my time, but of course we could use degrees and hours if we wanted to, in which case the angular velocity of the Earth would work out to be
a 15 degree per hour drift.
Thanks, Bob.
The radius b, again, is 6.4 times 10 to the 6 meters. Omega is 7.27 times 10 to the minus 5 radians per second. And recall from your trigonometry that the word radian is just sort of a bookmark. Radians are dimensionless units. Omega is really, if I want to think of it that way, 7.27 times 10 to the minus 5 reciprocal seconds. The speed is the radius of the circle times omega, which works out to be about 465.42 meters per second. Or if you prefer imperial units, it's about 1,041 miles per hour at the equator. I wanted to calculate this for two reasons. Here's the first one. In the flat Earth movement, a common debating tactic is personal incredulity, by which I mean there is some fact, and the person who doesn't want to believe in this fact says, basically, do you expect me to believe that? Relative to the center of the Earth, a point on the equator is moving about 1,041 miles per hour. Our flat Earth friends say that's obviously absurd because one would be flung out into space. Let's look at that. The magnitude of the acceleration caused by this circular motion is easily calculated. This is speed squared divided by radius, which works out to be 3.38 times 10 to the minus 2 meters per second squared. Since of all of these circles, the radius is largest at the equator, this is the largest acceleration of this type that you'll see. We can now answer the question, why doesn't water and other things get flung off into space if they're moving at over 1,000 miles at the equator? The answer is the acceleration due to gravity is 9.8 meters per second squared, and this tendency to get flung out into space corresponds to an acceleration of 0.038 meters per second squared. Since 9.8 is much bigger than 0.038, the question has been satisfactorily answered. Or, to be more dramatic, as our friend Desertfile might say,
Gravity, gravity! Have you ever heard of gravity? Gravity! Gravity!
I wanted to bring this up because when we finish this chapter, which will be in the next video, we're going to see something called curvature, and it's going to look very much like something that involves moving around in a circle at constant speed. I hope everyone's having a good day, and I'll talk to you again soon.